Good morning. Welcome to this case study on five-phase induction motor. We are all familiar with single-phase induction motor and three-phase induction motor. Phase is more than two. We call it as multi-phase induction motor. So the best examples for multi-phase induction motors are three-phase induction motor, two-phase induction motor. But in the market, we don't have anything as two-phase. If you take up multi-phases, anything more than two. So a phase is normally, right, it is going to be what is available in the market is more than three phases. It could be a four-phase induction motor, or it could be a five-phase induction motor, or six-phase induction motor. Like if you take up the need for multi-phase induction motors, they can be very well used in propulsion systems where a very high torque is needed. Like high torque is needed. This example is going to be a ship, or it could be a aircraft, or it could be a compressor units. All those systems, they require very high propulsion torque. And if you take up the multi-phase machines, the type of torque, the type of inverter they use, right, it is going to be different, and it all depends upon the phase of the machine that we consider. And if the phases are higher, automatically per phase power requirement in the inverter is going to be very low, and current per phase also it is going to be very low, and it will improve the electrical and mechanical properties of the machine, and you can achieve a very high torque because the number of phases are very high. You can achieve very high torque and efficiency. This is a picture of a five-phase machine where you have a DC link voltage given to an inverter, and if you see a five-phase inverter, five legs you see it, and you see a winding also of five number of phases. And if you take up the five-phase induction motor, the operating principle is going to be similar to that of a three-phase induction motor. How a three-phase induction motor works, the same principle is applied over here also. You may wonder what is going to be the difference. The difference exists in the winding arrangement. And normally, in the case of a three-phase machine, between two phases, there exists a 120-degree phase difference. But here, the coils are going to be separated by 72 degrees. How the 72 degrees arrives? 360 degree divided by number of phases. Here, the number of phases is 5. So 360 degree divided by 5, it gives you that 72 degree. So 72 degrees is the phase difference between one phase to other phase. And if the phase number is very higher, automatically, right, the angle of separation is going to be lesser. That's the difference. Like in three phase, how we connect the stator windings in star fashion and delta fashion, the same way. Here also you can have a star connection, you can have a pentagon connection, you can have a pentacle connection. All three types of connections are possible in five-phase induction machine. And definitely there is going to be a difference in the voltage level also. If it is going to be a star connection, your line voltage and phase voltages are going to be equal. If it is going to be a pentagon connection, your line voltage is equal to 1.1756 times the phase voltage. If it is going to be a pentacle connection, it is going to be 1.902 times the phase voltage. So you can get a very high voltage, nearly two times the phase voltage in the case of pentacle connection. And if you take up the input power calculation and output power calculation, it is similar to that of three phase only. In three phase, how we write the input power? It is 3 into Vi cos phi. The same way, here also it is going to be 5 into Vi cos phi. The mechanical power also, power equivalent also, when you write it as 3 into your number of poles into your V1 square into R2. So the same concept, it is being used here also. And you may wonder how the torque slip characteristic it is going to be. It is similar to that of a three-phase machine, but the only change is the level of output, the level of torque that is established is going to be different. In the case of star connection, if you see, we know that line voltage is going to be equal to phase voltage. So you get a torque. You get a torque here, and if there is a failure in any one of the phase, right? If you have one phase being absent, automatically the torque is going to be reduced. And like if you see, we all know torque is directly proportional to your applied voltage, square of the applied voltage. So if you have one phase absent, then automatically the reduced reduction in torque will be around 36%. If you have two phases absent, then automatically you'll have subsequent decrease in the torque value. That is very clear over here. In the case of pentagon, with all the phases existing, you get a very high torque compared to star connection. And the similar concept is going to be applicable here also. If there is one phase absence, automatically your voltage level is going to decrease and your torque level also is going to decrease. In the case of pentacle connection, it gives a very high torque compared to all the other two methods. And here also, when there is one phase absent, the torque is going to be quite higher than the other two methods. And pentacle connection is normally preferred, like for high propulsion units. So whenever we use a high propulsion system, for that you can go with a pentacle connection, and for laboratory and all, we can go with a star connection. Thank you.